This is question 8 on the HL paper, and it's also question 5 on the SL paper, and it's about solar radiation. So it's about topic 8, energy production. Okay, first question, unfortunately most people got wrong. It stated the Stefan-Boltzmann law for a black body. If we go to topic 8, we have a look at some of the formulas that you see on the formula sheet. You can see that the Stefan-Boltzmann law is right there, and it's the power radiated is equal to the Stefan-Boltzmann constant multiplied by the surface area of the body multiplied by the temperature to the power of 4. You can write down the formula as long as you define some of the symbols. You don't need to include that emissivity because the emissivity of a perfect black body is 1, so we don't really include that for this topic. But most people wrote down something about black bodies absorb and emit radiation perfectly, something like that. But that's not the Stefan-Boltzmann law for a black body. If you did need a hint, part B and the rest of the question really was all about using the Stefan-Boltzmann law. So BI, using the data from this table, show the power radiated by the sun is about 4 times 10 to the 26 watts. You have to use the Stefan-Boltzmann law. Again, emissivity is 1, so we don't include E. E's not included. You'll learn that in your lessons. Multiply the rest together. Remember, this area here is the surface area of a sphere. So we had a couple of people messed up. That's 4 pi r. So that's a surface area of a sphere we're meant to include right here. That's 4 pi r squared, sorry. Multiplied by the temperature to the power of 4, and we get 4 times 10 to the 26. So that's just applying the Stefan-Boltzmann law. Second part is to calculate the solar power incident per unit area at a distance from the sun, which is equal to the Earth's distance from the sun. So we're looking at how much solar power we get from the sun. And the way to do this is to work out a ratio of the incident area, the area that the sunlight is going to hit, versus the total surface area of a sphere, which has a radius of the distance from the Earth to the sun. So imagine the orbit that the Earth is in. Imagine that was part of the circumference of a sphere. You work out the area of that sphere, and then you work out the surface area of the Earth that the sun will be impacting. So it gives us the radius of the Earth, and we need to work out it's basically the cross-section of the Earth, so the cross-sectional surface of the Earth. And we get 1,400 watts per meter squared. If you're not sure how to do that one, ask your teacher. The next part is about working out the average power absorbed per unit area at the Earth's surface. And to do this, we can find out it's 240 watts per meter squared. But why is that value different from this value? Well, partly there's a number of reasons, but 3 reasons you can get marks for is that the albedo of the Earth means that some of the radiation is reflected, particularly the oceans and poles especially. Poles have reflected a lot of that energy. Earth's surface isn't always normal to the incident radiation, so as you can see on my handy little diagram here, a solar panel, for example, would receive more energy per meter squared here than it would up here in the northern or southern latitudes, which is why up here we have solar panels angled so that they'd get more sunlight. And a third reason might be that some energy is lost as radiation travels to the Earth. That's in the space between the sun and the Earth. You can get a maximum of 2 marks for that. Part 4, again, is Stefan-Boltzmann law. And it says to show that the value for power absorbed per unit area, in this case per meter squared, is consistent with an average equilibrium temperature for the Earth, about 255 kelvins. Ignoring the fact that that's not the average equilibrium temperature, it's just to show that it should be about 255. And there's 2 ways you can do that. You can either use that 255 Kelvin to work out an answer close to 240, or you can use 240 and evaluate that answer to get an equilibrium temperature of about 255. Either way is absolutely fine, but you have to show you're working. You can't just write one half of an equation and then write equals about 240. You have to do that. You have to show that you've done the equation, done the formula, and write down the answer with a decimal place or two wrong, and then show that that is about the answer. So you've got to do a calculation there. You can't leave that blank. Part C and Part D, there's a little bit of leeway here if you put things in the wrong box, but essentially there is a correct answer for each. Explain, by reference to the greenhouse effect, why the average temperature of the surface of the Earth is greater than 255. Well, it's the greenhouse effect. So radiation from the sun is re-emitted from the surface at longer wavelengths. Those long wavelengths are absorbed by greenhouse gases. You don't have to mention particularly which one. And some of that radiation which was absorbed is re-emitted back to the Earth. And that's why the average temperature of the surface of the Earth is greater. It's getting a double dose. Part D, and finally, suggest why the burning of fossil fuels may lead to an increase in the temperature of the surface of the Earth. Well, name a greenhouse gas, but more CO2 or some other greenhouse gases can be released into the atmosphere. That leads to an enhanced greenhouse effect because there's more radiation of energy towards the surface, like you discussed in Part C. So there's a little bit of leeway here, and there might be a few other marks you could pick up depending on how you phrased your answers and how you wrote your answers. But this is what the mark scheme's after. So we've got to be quite specific that we're answering the question that was asked. A lot of you rambled a little bit too much and essentially went off script and went away from the question that it was asking. So those are the answers. Those are your 15 marks. And that's it.